All right, well, in this lecture, we're going to work on calculating the energy and the power of discrete time signals. And I have these three examples here, and I have circled the ellipses in each case. And I just want to say a couple things about these ellipses. They are there to tell you that the signal continues how you would expect it to. So you just have to take your best guess on what me or the textbook is expecting you to think here. So in the first example, we have 0, 0, 0, and then the ellipses. So you can guess that the signal is going to be 0 for the remainder of time. And over here, same thing to the left, that the signal is going to be 0 for the beginning of time, way out here at minus infinity land. And for example 2, we've got a constant signal, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then you can expect it to just continue 1, 1, 1, 1, 1, 1, 1 to the right and also to the left, 1, 1, 1, 1, 1, 1, 1. For example 3, we've got zeros at the left, so you can expect it to remain 0 to the left. And to the right, we've got 0, 1, 2, 3, and so you can expect it to continue on that way, 4, 5, 6, 7, and so on. All right, having said all of that, we're going to work on example 1 right now. We're going to calculate the total energy in that signal, and that was n equals minus infinity to infinity, the sum of the absolute value of the signal squared. Now, in all three of my examples, the signal is purely real, right? So example 1 takes values of 1/4, 1/2, and 1, and 0. Those are purely real numbers. And in example 2, it just takes on the value 1. That's certainly a purely real number. And same with example 3. So what I can do right away then, because it's a purely real signal, is drop the absolute value and write it like this. Now, my signal is 0 to the left of minus 2, so squaring it contributes nothing to the sum. Squaring 0 remains 0, and then adding 0 contributes nothing. To the right of 2, it's also 0, and so squaring it remains 0 and contributes nothing to the sum. So I can write this not from minus infinity to infinity, but from minus 2 to 2 of our signal squared. Okay, and now I can evaluate this. Well, this is called expanding the sum. So when n is minus 2, the signal is 1/4. So I would have 1/4, and then we need to square it, right? Because our energy is to square. Then when n is minus 1, I have 1/2, and I need to square it. And when n is 0, I'm at 1, and I need to square it. And then I have a 1/2 that I square, and a 1/4 that I square. Okay, and that was the n equals 2 term, and so those are the only 5 terms here that can contribute energy, right? Non-zero energy. Okay, so I can plug this into a calculator, or whatever you need to do. 1/16 there. This is actually 4/16. This is 16/16, 4/16 again, and 1/16. So if I add up all the 16ths, I get 24, 25, 26. Is that right? 26 over 16. And so there is a 2 there. This is 13/8. So that's my total energy, 13/8 in that first example. So let's talk about its power now. The power was the limit as this capital N, some capital N goes to infinity, of 2 times that capital N plus 1 times n goes from minus n to plus n of the absolute value of xn squared. Okay, so I'm going to write that like this. I can break it up as the limit as n goes to infinity of 1 over 2n plus 1 times the limit as n goes to infinity of a sum, n goes from minus n to plus n, of xn, like this. But the reason I'm breaking it up like that is because we just calculated this sum, right? That's exactly the energy in the signal. You see, as the bounds become minus infinity and plus infinity, I get exactly this expression here. And so I know that this in red is 13/8. So this becomes the limit as n goes to infinity of 13/8 over 2n plus 1. Now there's nothing in the numerator to cancel that denominator n, so as n goes to infinity, I've got a number divided by something that gets larger and larger, and so this goes to 0. That is the power averaged over all of time, 0. Of example 1. Again, feel free to pause the video, but I'm gonna move on. Okay. And we're going to go to example 2. Now example 2, calculate the energy, is again purely real, and it goes on forever, so I'm going to have to calculate this sum, and my signal here in this range from minus infinity to infinity is 1, and when you square 1 you get 1 back. So I'm just going to write 1 there. So what do you get when you add 1 infinity times? Oh, you get infinity. Yeah. So we're kind of sad that we didn't get a number there. We have infinite amount of energy in example 2 because it goes on forever. But let's calculate its power averaged over all time. So that is the limit as this some capital N goes to infinity of twice that capital N plus 1, n equals minus n to n of 1. Okay, so now we're not quite sure, right? Because we have this sum goes to infinity, but then this thing gets divided by infinity, so we're not sure what happens there. But the key is this guy. Let's consider for some finite n what the sum is equal to. So I'm gonna draw the signal here again, even though I have it over here as well. But let's say n is just 2. So if I add the number 1 up from minus 2 to 2, how many, what is my sum? So that would be 1 plus 1 plus 1 plus 1 plus 1. So that would be 5. Right? When n is 2, this sum is 5 because you're adding up 5 1s. When n is 3, so if I extend to 3 there and minus 3 on the left, then how many 1s am I adding? Well, I'm adding 1, 2, 3, 4, 5, 6, 7. My sum is 7. So, and we discussed this in a previous video. This becomes the limit of 1 over 2n plus 1, but the sum is just 2n plus 1. Right? That's the number of 1s I'm adding up here. Right? Because here n was 3 and I had 7. My sum was 7. Here n was 2, my sum was 5. 2n plus 1. So now the 2n plus 1s cancel, and I'm left with the limit as n goes to infinity of 1. Well, that's just 1. So in this case, for example 2, I have infinite amount of energy, and I have 1 unit of average power. Okay, finally then, example 3. I'm going to calculate the energy of this guy. Okay, and that is, again, the sum from minus infinity to infinity of the absolute value of the signal squared. However, again, from the left of the origin, the signal is 0 and contributes no energy. So I can just as well start my sum from 0 to infinity. And here, the signal, okay, I'm going to use math to model this thing as it increases. So for any n, what is this? How is this signal growing? Well, it grows with n. If n is 1, the signal is 1. If n is 2, the signal is 2. If n is 3, the signal is 3, and so on. So my signal is n. And then when I square it, because I have to square it according to the energy formula, I get n squared. So I have this sum here, and you should have seen this in your math class. Okay? The sum of n squared from 0 to infinity, there's a formula for that. Right? And excuse me, actually there's a formula for it when the top bound is not infinity, when it's a finite number. For this one, so this is like adding 0 plus 1, then when n is 2, this is 4. When n is 3, this is 9, and so on. So what is that equal to? Well, that is equal to infinity. Okay, so again, our signal here has infinite energy. But let's look at the power. Okay, the power is defined as the limit as some capital N goes to infinity of 1 over 2n plus 1 of n equals minus n to n of our signal squared. Now, I have to work on that sum a little bit. That sum, for negative values of n, that sum is 0, or the signal is 0, so it contributes nothing to the sum. So I might as well just take 0 to n. 0 to n, and in that range, again, my signal is n, right, in blue. My signal is n, so when I square it, it becomes n squared. Now, for the moment, I have a finite number, capital N, up there on top. Now you've seen this formula in your math class. That sum is equal to n times n plus 1 times 2n plus 1. So if you were making a formula sheet, this might be a good formula to have, divided by 6. So that sum is this thing here. N times n plus 1 times 2n plus 1 over 6. That's from math class, and I'm not going to derive it here. The question is, what happens to the power then? What happens in this limit? And so this 2n plus 1 cancels with this 2n plus 1, and we're left with the limit as n goes to infinity of n times n plus 1 over 6. Well, there's nothing in the denominator now to cancel this growth in the numerator. And so that's just infinity. And so we're kind of sad that it didn't converge. So this signal, example 3, has infinite energy and infinite average power.